Hello everybody. Today I'll be talking about 6.4, the central limit theorem. We went over 6.3 towards the end of class. So let me kind of jump into it. You have the slides. The first one looks like this, the central limit theorem. But we're going to kind of read it and then go from there. It says, for all samples of the same size n with n greater than 30, the sampling distribution of x bar can be approximated by a normal distribution with the mean, mu, and standard deviation of sigma divided by the square root of n. So that means central limit theorem is big. So if you have an original population that we'll just say, if these are the population, is normally distributed, okay, and I have samples from this population, what the central limit theorem is saying is a couple of things. This has a mean of mu and a standard deviation of lowercase sigma. So if I took samples, averages of these, what would happen, according to the central limit theorem, is that my sample averages will be approximately the same, where the mean of my sample averages, the mean of my sample averages will be approximately the same as the actual mean of the population. So what does this tell us? If I take all possible samples of some size n that's greater than 30, okay, which was another thing that you want to pay attention to is the sample size. If it's 30 or more, we can assume that the sampling distribution will be normally distributed, which would be an important side fact. From here, not only do we get a normal distribution for our sampling distribution, we also will notice that our variance actually decreases. By how much does it decrease? By the standard deviation of the sampling distribution of x bar will actually decrease by whatever the original was divided by the square root of n. Now this isn't limited to if your normal population is normal, or your population distribution is normal. What if you had kind of this skewed right curve? Well, and that had a mean, we'll call it mu, and some standard deviation. Well, what's the sampling distribution? So the bottom is the sampling distribution. So let's just say I took samples of size 40. And of those samples, most of my samples will fall around the mean. A few will be higher, and then a few will be lower. But overall, even if it comes from a skewed right population, the sampling distribution will still be roughly normally symmetrical or normally distributed, with, again, the mean of all the possible x bars of size 40, we said, will be the mean of the population. Also, the standard deviation of those means in my sample will be the original standard deviation divided by the square root of n. Okay, so that's the calculation. And final example, I'll kind of show, even if it comes from a roughly uniform distribution. So if I got random samples from a uniform distribution, what would a sampling distribution look like? Well, this could be kind of like your dice example, 1 through 6. What's the average? If we were to collect samples from the class of 30 rolls, what would the average die roll be? Well, it would be somewhere about 3.5, which is what the actual the actual probability would be the low plus the high, 1 plus 6 divided by 2. So it'd be about 3.5, somewhere here. So how would the distribution of samples of size 30 look? Well, even from a uniform distribution, this would look, the mean would be here, and this has its own standard deviation, but the mean of the sampling distribution, the distribution of sample means of, let's say, size 40 again, would be there. But not only that, the variance or the standard deviation of the sample means would be the standard deviation divided by the square root of n. So what we gather from this is that it doesn't matter what the original population shape is, according to the central limit theorem, if the sample size is greater than 30, the distribution of sample size greater than 30 of the means will tend to be the mean of the population. So the mean of the mean of the sample means will be the population mean, as long as n is greater than 30, regardless of the shape of the original population. Furthermore, for all three cases, it's the same. Okay, for all three cases, the same. Okay, so I think that kind of covers the central limit theorem definition. And then if you look at the next slide, you'll actually see a picture of some maybe original data. I think it's a histogram of the sampling distribution of a normal distribution, more of what I kind of showed here. So I'm going to kind of look at the central limit theorem and the sampling distribution of X bar. Okay, this here. So it says a couple of things that I've kind of already mentioned. The population has a mean mu and a standard deviation of sigma. Simple random samples all of the same size n selected from the population. The mean of all values of X bar is denoted by this notation, mu sub X bar, or really it's the mean of the sampling distribution. But what they do tell you is that the mean of the sampling distribution equals the mean of the population. That's important. Okay, the mean of the sampling distribution equals the mean of the population. Also, what they tell you is the standard deviation of the sampling distribution is the standard deviation of the population divided by the square root of n. Okay, so these are two important relationships that we need to understand. Now, what if, now I'm moving on to the next slide. Okay, what if your original population is not normally distributed and n is less than or equal to 30? If n is greater than 30, you're covered. You're okay. Because of what we've shown here. The sampling distribution will be normally distributed, so we're okay with that. But what if it's not normally distributed and is less than 30, and is less than or equal to 30? So the distribution of X bar might not be approximated well by a normal distribution, and the means of this section might not apply. Use other methods such as non-parametric methods. So, and we may get to that or may not. But what are the requirements? When working with the mean from a sample, verify the normal distribution can be used by confirming that the original population has a normal distribution, or the sample size is n greater than 30. Determine whether you use a normal distribution with a single value x of the mean X bar from a sample of n values. See the following. So the individual, when working with an individual value from a normal distribution population, use the methods in 6.2, which is using the z-score. Okay. And then when using, if you're finding the mean from a sample of values, we're going to use an updated z-score with this standard deviation. So now it's X bar minus mu, and you'll see it there on your paper, but the z-score will be X bar minus mu divided by the standard deviation over the square root of n. That's with the sampling distribution, but we'll see values of that. Then the next slide is just notation, which I think we kind of already covered. Okay, so I'm going to kind of go move ahead to the pulse rates of women. So we're actually going to apply some of these ideas and be able to use that to help us answer questions that you're going to see. Okay, so for the first question, it says in the chapter problem, it was noted that women have normally distributed pulse rate with mean of 74 beats per minute and a standard deviation of 12.5 beats per minute. Find the probability that one randomly selected woman has a pulse rate greater than 80 beats per minute. This we actually covered in section 6.3 in class, or 6.2. So in this case, it's not new. There's a normal curve. They tell us it's normally distributed with a mean of 74 and a standard deviation of 12.5. So I can, and I'm looking for 80 or greater. So I can shade in this direction, 80 or greater. So if I'm looking for 80 or greater, you can use the table, but as mentioned in class, I told you my preferred method is use the calculator. So if I use normal CDF with the lower bound of 80, an upper bound of infinity, so I'll put E99 as infinity, and a mean of 74, and the standard deviation of 12.5 according to this problem, I will get, I realize that's not the brightest, I won't write with that color anymore, but if I input that into the calculator, we'll get our answer. Okay, and feel free to pause it. I went ahead and entered into my calculator. If you want to try it before I do it, kind of like we do in class, I think that's probably a good method with this online teaching here. So the probability that X, a single individual, is going to be greater than 80 equals 2. If I input normal CDF of all this, I'm going to get 0.3156. And again, you can round to the third decimal or the fourth decimal. Either way is fine. If I asked it on a test, I'll specify specifically how many. Okay, so I wrote to the fourth here. Okay, so that answers A. Let's move on to B. So now B says, find the probability that a sample of 16 randomly selected women have a mean pulse rate greater than 80 beats per minute. So this is not the same question as before, because they're not asking for one person being greater than 80. They're asking for the mean of 16, I'm sorry, to be greater than. So this is actually a distribution. One, why can I assume normal distribution? The original population is normal. So it, even though my sample size is 16 or not greater than 30, I can still assume that my sampling distribution of what size, all possible samples of size 16, all the possible averages will be distributed normally. Why? Because the original population came from normal distribution, as stated in the problem. It tells you, it says women have normally distributed pulse rates. So now that we have established this, you'll already see that there is somewhat of a difference between A and B. A, and maybe I should put X bar out here as the label of means. Okay, A is a single value of one woman. B has values of the means of 16 women, the possible means of 16 women pulse rates. So according to this, according to the central limit theorem, the mean of this distribution should be the same as this mean from the population. Okay, so then that mean would be 74. And also according to the central limit theorem, the standard deviation of the sampling distribution should be the original standard deviation. Here, let me use the formulas. That should equal the population mean, which is 74. And then the standard deviation of the sampling distribution will be the standard deviation of the original divided by the square root of n. Okay, so this is the change. The standard deviation is 12.5 divided by the square root of n, 16. So this is my new distribution. And I'm going to be quite honest with you, I usually don't even calculate this number. Unless for some reason I ask you for the number here, I usually just leave it like that. But so now I have my new distribution of sample means of size 16. Here it is. But in this question, what am I asking? We're asking, what's the probability that a sample of 16 randomly selected women have a mean pulse rate greater than 80? Well, I'm going to do kind of a similar thing. 80. And if I were to make this more proportional, I probably would have squeezed this in because the standard deviation is going to decrease. Okay. In other words, make the normal curve thinner. But I'm interested in the probability. Right now, I'll squeeze this in here. Let me make sure you can see that. Probability that X bar is greater than 80. X bar being the sample mean of 16 females is going to have a mean pulse rate greater than 80. So then how are we going to do this? We'll take a similar approach. Normal CDF. Okay, but this time the lower, or actually, yeah, this time the lower is still 80. The upper is going to be still infinity, so that didn't change. The mean is still going to be 74 because they should be the same. The mean of the population should be the mean of the sampling distribution. And then the standard deviation should be the standard deviation of the sampling distribution, which you can literally type in this into your calculator. Okay, with the square root of, I don't know if you can see that, but there it is. Okay, 12.5 over the square root of 16. So then go ahead and do that, and I'll do the same. Okay, so hopefully you paused it and tried it out. But what I get, I'm trying to type this in, normal CDF. Remember, to get there, you get the second bars, 0.0274. Okay, 0.0274. So this is the probability that you're going to get a random sample of 16 adult females that has where the means are greater than 80 is 0.0274. So it's not a very high likelihood that you'll get 16 women to have a mean pulse rate greater than 80. But if you look at this, this is like 2%, close to 3%. This is close to 32%. Okay, this is close to 32%. So there's a big difference. But why? Why is there a difference? This is the probability that one individual has a pulse rate, a female has a pulse rate greater than 80, which you probably would consider maybe it has pretty good chance that there's going to be one individual that has the pulse rate. But now you get 16 individuals. The probability that you get 16 individuals with a mean pulse rate of greater than 80 is not that high, because now you're talking about a group of 16. And better illustrated would be if I drew this as I mentioned earlier. The standard deviation would decrease, so then that means that this normal curve would be a little tighter this way, and 74 would remain here. 80 would remain there, but notice if 80 is here as compared to here, this is about 31%, 32% if we just say, and that would be about 3%. So this better illustrates it, because what happens, the standard deviation is going to decrease for a sampling distribution of 16. And also logically, 16 people having that high of a pulse rate is not likely. Okay. All right. So we have one more on that one. It says, given that part B involves a sample size that is not larger than 30, why can the central limit be used? And I kind of already mentioned that. Why can it be used even though this is sample size of 16? Well, the problem tells us the original population was normally distributed. That's why. So if your original population is normally distributed, then you are free to use this central limit theorem to calculate. Okay, so let's move on. In the next slide, you'll see it there. That's kind of more, it kind of shows you this question. And there's the 30% from A, and then the 3% from B. Okay. And then following that, it says, how do we identify significant results? There's this slide again. The rare event rule for inferential statistics. If under a given assumption, the probability of a particular observed event is very small, and the observed event occurs significantly less than or significantly greater than what we typically expect with that assumption, we conclude that the assumption is probably not correct. So, meaning if we said that the mean pulse rate, so let's say there's an assumption that the mean is 74, right? And somebody took a sample to test this, and they said, okay, I took a sample of 20, and the mean pulse rate that I got was, or let's say with this, I took a sample of 16, and the mean pulse rate I got was 80. Well, that would challenge the known idea that the mean pulse rate for women is 74. You might think, well, that's not that far off, but if it happened to be 80 in some study for 16 women randomly selected, that would challenge the fact that we think it's 74. Why? Because it's such a small chance that you get less than 5%, right? It's such a small chance that you'll get 80 or more for groups of 16 women randomly selected that I'm going to start to question whether this is true or not, whether the original is true or not. So that's kind of seeing if you get significant results. That's just as an example, okay? But we'll have more in a bit. Okay, so the next slide. Assume that the population. So this is human body temperatures, and I'm going to set that one up, and then we'll talk about it. Okay, so now I'm looking at this example for human body temperature. So we're going to read that. Assume that the population of human body temperatures has a mean of 98.6 degrees Fahrenheit, as is commonly believed. Also assume that the population standard deviation is 0.62 degrees Fahrenheit, based on the data from University of Maryland researchers. If a sample size n equals 106 is randomly selected, find the probability of getting a mean of 98.2 degrees Fahrenheit or lower. Okay, so here we got to look at two things. The distribution of the population is given to us. The population is 98.6 degrees Fahrenheit on average, and the standard deviation is 0.62 according to this problem, so it's normally distributed. But the question is asking for a distribution of the sample means, which we know from before that the mean, so this is a distribution of our population of X. What about distribution of X bars? The distribution of X bars we know is the same, okay, from the central limit theorem, and the standard deviation of our samples are going to be the standard deviation of the population divided by the square root of n. Okay, so in this case, the only thing that changes is this should be divided by the square root of, in the problem they said the sample size is 106, square root of 106. Okay, and like I said, I usually don't even calculate that. We can, not really necessary. So from here, if I answer the first question, which says, which is in the problem, so if a sample size of n equals 106 is randomly selected, find the probability of getting a mean of 98.2 degrees or lower. Okay, so I'm going to draw my picture, and I'm only going to draw the sampling distribution. So here's my x bars, and I know my mean is 98.6. I'm going to go ahead and write in what I need, which is 98.2. Would be a little bit to the left of that, about right here maybe. Just write 98.2, and then it says less than, so I'm interested in area to the left. Okay, so I pretty much have it. I would just use my calculator from here. Again, normal CDF. Okay, what's my lower? Well, what's left of this? Negative infinity, or negative E99. What's the upper? It's 98.2. What's my mean of my sampling distribution? This one, 98.6. And then what's my standard deviation of my sampling distribution? 0.62 divided by 102, since this is for a sample size of 102. So if I input this, I would get my probability. So that's what I'm going to do. Okay, so I input that into the calculator, normal CDF, and what I found was that the probability that x bar is less than 98.2 is a very small number, 0.000000000. One more, no, 1552. Okay. On your calculator, it shows up as 1.552 e to the negative 11, so that means move this decimal over 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 times. Basically, very, very close to zero, very small number. So my area is a little bit poorly represented. So I can adjust it or not. But if I were to kind of make a more accurate picture, again, the picture is just for a guide to sketch. But if I were to make a more accurate picture of that area, it would be 98.2. By the time I found the area, the picture served its purpose. Okay, it told me the lower bound, the upper bound, the mean, and the standard deviation. Okay, so it helped me out already. But that's an area very small. So what does that tell us? If you get a mean from a sample that of size 106, of anything less than 98.2, of that's going to be very, very, very unlikely. Okay. So, which is evidence to support that our mean temperature for humans is 98.6. Okay. If it was a high probability, then I might start to question our 98.6. Okay. So that answers the first one. There's follow-up questions. It says find the probability that the problem that an individual has a temperature less than 98.2 degrees. So this is a group of 106. So now we want the probability that an individual is, where do I do this? I could do it right here. This would be A, right? I'll call this one A. I'm gonna call this one B. Okay, so the probability that an individual. Okay, so individual, actually, I'm using this distribution, the original population, so 98.6 with the standard deviation of 0.62. So with this, I'm going to use pretty much the same lower. The lower is still going to be for 98.2, still going to be negative infinity. The upper is going to be 98.2, and then the mean is going to be 98.6, but this is where it changes. For an individual, I want the distribution of the population. Now here's the thing. I could actually use an individual as a sample size of 1, so I can use 0.62 divided by the square root of 1, which in fact gives me the same exact thing, 0.62. So there's 2 ways of thinking of that. Input that into the calculator and you answer it. Okay, so I wrote this here. Once I put this into the calculator, I got the probability that an individual has a temperature of less than 98.2 degrees is 0.259, which is actually a pretty good chance that somebody would have a temperature less than 98.2 degrees. Think about it. If I sampled 100 people, it's not that unusual that one individual, or if I sampled one person, it's not unusual for one person to have a temperature of less than 98.2. Where it's unusual is if you have a group of 106 people to have temperatures that extreme, because it's 106 persons against one. Okay. All right. So we'll answer some of the follow-ups, but I'm going to clean the board up real quick and come back. Okay. So now I'm on this slide. So we're going to find the probability of one randomly selected human having a body temperature higher than 100. So 100 degrees is pretty high. So we're going to assume it's 1, right? So which one are we going to use? X or X bar? Well, this is with 1. So we're going to use X. So we're going to use that distribution. So I'm going to draw my picture. The mean is 98.6, and I'm interested in the probability that some randomly selected person has a temperature higher than 100. Okay, a randomly selected person, temperature higher than 100. So I'll call this problem C on that set. In this case, I would do normal CDF again. Mean is, or the lower is 100. This time upper, the area extends to infinity. So e to the 99. The mean is 98.6, and the standard deviation is, since it's an individual, I'm using original population 0.62. Input into the calculator and we have an answer, and that's all there is. Okay, so I input it into my calculator and I get 0.0119 rounded up to 0.012. So in this question we found the probability that an individual, X, not X bar, is 0.011 or 0.012. No, wrote that incorrectly. Probability that an individual is greater than 100 degrees temperature Fahrenheit is 0.012. Okay, so we'll do the next question as well. It's a similar question, but this time it says find the probability of 5 randomly selected humans having a body temperature higher than 100. So already with 1, it was kind of rare, right? It was 1% chance of having one person higher than 100 degrees Fahrenheit. So what do you think it's going to be if I get a sample of 5? What's the probability that their temperatures will all have a mean of 100 or more? So think about that, and then we'll actually calculate it. But the calculation here, again, we're using a normal distribution with the same mean, 98.6, and we're interested in the value of 100. But if I wanted to do this some justice, actually, I would kind of use like a similar distance here and here. But what I would actually do would be narrow down this normal curve because the standard deviation decreases, and we're actually interested in this. And you could visually see that the probability appears to be slightly smaller. So then what would we do? Normal CDF again. So we're going to do normal CDF. Lower is 100 still. Upper is infinity. And the mean is still 98.6. And the standard deviation, this time, we're not using an individual, we're using the sampling distribution, but not for 106, for how many? For 5. So I'm going to write 0.62 divided by square root of 5. Okay, that's what I didn't put into the calculator. So we'll input that and then we'll get our answer. Okay, so what I got was the probability that a sample of 5 is greater than 100 degrees Fahrenheit is 0.000000222. Okay, very small number. So again, solidifies the fact that the chance of having a group higher than 100 is much less likely than having an individual of getting higher than 100 degrees temperature Fahrenheit. Okay, so I'm going to kind of clear this out and I'll work on the next two. Alright, so the next two are kind of similar. It says find the probability of a random person having a body temperature between 98.2 and 100 degrees. So we're going to draw that picture. It's an individual, so think about which distribution am I using? Am I using the population or the sampling distribution? Individual, you can use the population. So the mean is 98.6. I'm interested in the interval from 98.2, which just says right there, all the way until 100 degrees, which we can say is about right here. And we're interested in the probability that it's between those two values. So I'm interested in this area. Okay. So how would I do this? Same as we did before. We would take normal CDF. Okay. And the lower would be 98.2 this time. It's the lower part of the area. Up in the upper would be 100. And then the mean would be 98.6, and the standard deviation would be 0.62 since it's for an individual. And let me go ahead and set up the other one too. So this is if that was C and D, we're on E. Okay, so E, we'll call it E, and then F is the follow-up one, which is a similar question. Find the probability of 8 randomly selected humans having a body temperature between 98.2 degrees and 100 degrees. So I'll try to draw it on a similar scale. 98.6, we'll go 100 about here, then 98.2 about here. But since it's the sampling distribution is for 8 people, I will kind of narrow my normal curve in this way, okay? And I'm still interested between 98 and 100. So there it is. That's what I'm looking for. And for this one, we're still going to do normal CDF, and we're still going to do the lower bound, 98.2, and we're still going to do the upper bound of 100, and the mean is still going to be 98.6. But what is the standard deviation? Well, this is for a sample of 8 randomly selected humans. So this is normally distributed with a mean of 98.6, but a standard deviation of the population divided by the square root of the sample size, 8. So that's what the standard deviation will be. So that's what you could input on for both of these. So which I'm going to do, and then we'll come back. Okay, so I went ahead and calculated both of these, And so now we'll write it in probability notation. So the probability that a randomly selected human has a temperature between 98.2 and 100 equals to, I get, let me make sure I got the right one for each one. Uh, 0.729. 0.729, and then over here, okay, give me a second. Okay, so this is good. And then on this problem here, we would, in a mathematical notation, we would say almost the same thing. The probability that a random sample of, how many individuals was it on this problem? 8 individuals is between 98.2 and 100, written this way, equals to, after putting in a normal CDF, I get 0.9659 rounded to 0.966. Okay, 0.966. Okay, so those are our two respective probabilities. And here, just a quick note, since the sampling distribution shortened the variance or the standard deviation, more was contained in the same interval. That's why the probability is now higher than this probability for an individual between two. Okay, one more follow-up question here, and then I'll pause it to kind of clean up the board a little. Okay, so it says, which we've done these questions already, find the body temperature that is at the top 10%. So again, I'll start with the normal curve. Top 10%, I'll draw that in, maybe this amount. Now problems like this lend itself to using either your table, you find a z-score of that process, and then you plug in your mean and your standard deviation, and you get the z-score from the table. But that's a long process. I prefer just using inverse norm of, remember the calculator can only tell you area to the left, but we're looking for the x value. Okay, so the calculator will ask you, okay, what area is to the left of your x value? We're going to tell it 9.9, 90%. And then it'll also ask you, what's the mean? Okay, the mean is the temperatures is 98.6, and the standard deviation, since I'm looking for an individual, is 0.62. And that's all I have to tell the calculator, and I will get my result. So hopefully you tried it, and after you input it into the calculator, what you get is 99, or we could say in a sentence, it's 99.39, but a temperature of 99.395 degrees Fahrenheit is the top 10%. You could also say 90th percentile, that's the same thing. Okay, so the last question looks similar, but it says, well, actually it is similar. Find the body temperature that is at the top 10%. Find the body temperature that is top 10%. What I meant to do, let's change it a little bit. We're going to find the body temperature of 8 randomly selected people being at the top 10%. Okay, so what does that mean for us? We're going to use not this distribution, but the sampling distribution for x bar. Meaning the mean is the same, it's still 98.6, and Okay, but the standard deviation, so it's normally distributed with the mean of 98.6. The standard deviation is 0.62 divided by the square root of 8. Okay, so just keep in mind, it's not on the problem. I changed it. It should read, find the body temperature of a sample of 8 people that is at the top 10 percentile. Okay, so given this, we're kind of doing exactly the same thing. We want the top 10%. Okay, so the top 10% of the area. So I want to tell, I want to know what that X bar is, so I want to tell the calculator inverse norm still. But again, not for this distribution, for this distribution. So which is going to be, I'm going to tell the calculator the area to the left of that would be 0.9 still. The mean is still 98.6. And the standard deviation will be 0.62 divided by the square root of 8, since it's with a sample of 8. And we input that and we'll get our answer. Okay, so I went ahead and did that, and I got, here we'll write it in a sentence, a temperature or a mean temperature, for 8 randomly selected people is 98.881 for top 10%. Or the 90th percentile. Okay, so that answers those. Okay, so we're going to cover 6.5. It's not too many. It's only a few slides, and really there's not much calculation that I'm looking for out of this. But let's start with this first slide, which talks about the normal quantile plot. So when trying to determine whether a collection of data has a distribution that is approximately normal, we can visually inspect a histogram to see if it is approximately normally bell-shaped. We can identify outliers, and we can also use normal quantile plots. So one of the big questions in stats is a data set normally distributed or not? Up until now, we kind of just looked at a histogram and we said, it looks normally distributed. It looks like a bell curve. It appears to be a bell curve. So in this chapter, or this section, we're going to kind of assess a little bit more carefully when to determine if something's normally distributed. Starting with this next slide, which you'll notice the first bullet says histograms, the construction of a histogram. If the histogram departs dramatically from a bell shape, conclude that the data do not have normal distribution, which is what we've done up until now. We look at it, does it appear normal? Okay, we'll call it normally distributed. So that's still a method. We're still going to use that. We kind of want to use all three, have a preponderance of evidence to conclude that it's normally distributed, because it allows us to do some of these other things that we have done in other chapters. The second method of determining if something's normally distributed, you can identify outliers. If there is more than one outlier present, conclude that the data might not have a normal distribution. Just one outlier could be an error or the result of chance variation, but it says be careful, because even a single outlier can have dramatic effect on results. So then let's say you do, how do you define outliers again? The whole box plot thing we did a while back. You have to find the mean, the IQR. If it's, I'll just give you the refresher, but you calculate what we call the lower fence, right, and the upper fence. Okay, So outliers fall outside the fences, and the lower fence equals Q1 minus 1.5 times the IQR, and then the upper fence equals Q3 plus 1.5 times the IQR. Okay, and then the IQR, I'll give you that, was calculated by just Q3 minus Q1. Okay, so anything outside that would be considered outliers, any numbers in a data set. That's the second method, the outliers. Third method is using the normal quantile plot. This normal quantile plot is basically from the previous slide. I didn't read the definition, but I guess we should. Is a graph of points x, y. Really, it's a graph of the data. So whatever your original data set is, you find the corresponding z-scores using this formula. Okay. So let's say you have a data set, and the data set is maybe people's siblings, right? Or number of siblings, and you have somebody with 2, somebody with 4, somebody with 3, somebody with 1, somebody with 4, and so on, 5, 8. Okay, now I want to determine if this data set's normal using a quantile plot. So these are my x's. Okay, and then what I would do is I would calculate the standard deviation. And once I get the standard deviation of these, I would sit there and use this formula 1, 2, 3, 4, 5, 6, 7 times. I would get z-scores, and then I would plot those z-scores. Okay, and I'm not going to do it, but that's how you would do it, because I'm not really going to ask you how to construct them. This is how you construct them. But what I'm looking for is, if I want to know if this data set of siblings is normally distributed, what would I want? What I'd want would be, if this is the x-axis, this is the z-axis for, remember what z-scores are. Z-scores are how many standard deviations above or below the mean something is. So if right here is 0, what do I really want? I want there to be some negative z-scores, some positive z-scores, but really what I'm looking for is a quantile plot that has some kind of linear shape to it. This is an indication that the original data set is normally distributed. Okay, so again, I won't really ask you to construct these, but if we look on the next couple of slides here, I'm going to kind of just read this one. It says the normal distribution, the population distribution is normal if the pattern of the points is reasonably close to a straight line, as I stated, and the points do not show some systematic pattern that is not a straight line pattern. So it can't be this. This shows some other kind of like an exponential. It can't be that. It can't be, you know, like a parabolic shape or something like that. It can't be any other shape other than a linear straight line pattern. Also, the points do not lie reasonably close to the line, or not normally distributed if the points are more scattered and not close to the line, and also shows a systematic pattern. So here's kind of an example. On this picture, you'll see a data set, a distribution of original data, in this case for IQ scores, and the question, and then right next to it is the distribution for all those IQ scores as compared with their z-scores. So they sat there and they plotted all that. Now that quantile plot looks roughly linear. So therefore, that's further evidence. Well, just looking at the histogram, the histogram appears to be roughly symmetrical, roughly bell-shaped. You might question this little piece right here. Maybe it's skewed right, but even that's kind of a stretch. The quantile plot will kind of solidify our opinion on this and say this is roughly linear. Therefore, that's evidence to show that the original data set is normally distributed. So this is further evidence for that. The only one they didn't do was number 2, which was the outlier argument. Okay, so here we have another one, another original data set, clearly not normally distributed. Okay, so for each of the x values here, they plotted them against their z-scores, and you'll see that it roughly follows the line, but it holds a systematic curve, like a curve pattern that's not linear. Therefore, we would say this is not linear quantile plot, and we would conclude that this is not the original data set, not normally distributed, which if you just look at it, you would say duh, right, because it's uniform. Okay, so the final one here, you have one that appears a little bit more skewed right, but maybe somebody might argue, well, it looks bell curved. So okay, we get all these x's from the histogram, and we plot them against their z-scores, and we find this kind of curve here. So this also appears to have some systematic curve to it that is not linear. Therefore, we would determine that this original data set is not normally distributed. But again, the quantile plots helps to identify whether something is normally distributed or not. So you might be given, data sets like this where you have to make the histograms. But really more what I'm kind of focusing on is if I show you a quantile plot, do you have evidence to suggest it's normally distributed or not from the quantile plot? Also, can you determine if there's an outlier using the upper fence and lower fence from the previous sections? And also, can you look at a histogram and tell, is it normally distributed? And can you investigate further using those 3 methods? So that's all for that section, and that pretty much covers chapter 6. So again, we'll have our test next Thursday. I will see y'all then.